I thought a good place for us to start is talk about the basics of recursion. So recursion, in kind of a high-level description, is a way of defining a function in terms of itself. So in programming, we have this concept called a function. So for example, some programming languages, you'll describe all your operations enclosed within a function. Say you might know of the main function, say if we're talking about C or C++. You might be talking about inside of a class, such as having the main method, such as in Java. These are just some basic examples of functions and methods, or member functions, however you'd like to characterize these and however you would like to enclose them. But they'll have names and they have parameters to them. They also may return some value. So in programming, the way recursion functionally operates is that you call a function that is the same function. So it has the same name. It may have the same parameters. But the point is that you're taking a problem and you're solving a smaller aspect of the same problem instance. Just in the same way that when I carry out this process of solving the problem, I take the problem, I break it into a smaller chunk, and I call the function on the smaller chunk to proceed and incrementally solve the problem. So in some sense, it's kind of like passing the buck on to somebody else to finish working on it for you. So we'll see some examples of what I'm talking about here in a bit. Now, in terms of problem solving, which is I would argue is probably one of the most important elements of this, is thinking recursively about a problem gives you kind of a natural way sometimes to describe algorithms. So this is in contrast to talking about, say, describing an algorithm, what we call iteratively, that is using, say, for example, for loops, while loops. Imagine you traversing through some collection of some sort. The idea is that in those cases, you examine each member of that collection, one after the other. You may not think about things in the same way if you think about them recursively. And there's a lot of structures that are actually defined recursively, such as trees. Trees are a naturally recursive structure. So very often you'll find that algorithms that possess the structure of a tree, which many algorithms do, or many data structures that use the structure literally of a tree. I'm not talking about the trees outside that you look, they kind of go up like this. We're talking about the ones that in computer science we call, they're a type of data structure or families of data structures that have a root, and they're what we call rooted trees, and they grow downwards. That's at least how we like to draw them very often. But in such cases, it's quite natural to describe algorithms recursively. And we use this idea of recursion to do this. And what we call an algorithm that employs recursion, we call it a recursive algorithm. So just to make it clear why we might be like, Dan, why would you describe it like this if it's so darn natural? Is very often these algorithms are simpler to describe. So I'll say simple, often to describe. So just as a quick example, at some point I've talked about binary search. Now there's at least a couple different ways you could write out binary search. There's an iterative way for which you can imagine you have a while loop and you adjust two lower and upper parameters to nudge them closer and closer by having a subarray that you're examining over, and you always make a guess in the middle of that every time you nudge over one of the lower or upper parameters, and you keep repeatedly doing this until you find a match. Otherwise, you keep incrementally making the subarray smaller and smaller and smaller, which is characterized by these two variables, usually the lower bound and upper bound, something they called L and U in the algorithm, or upper and lower. And you know when you don't run into that element when these two cross over each other, meaning that the interval crosses. Now, you can describe the same thing using recursion by simply having it where you apply recursive calls instead, where the lower and upper parts, instead of them being simulated by these L and U variables, you instead have parameters in your recursive algorithm that you adjust if you want to examine the left half or the right half. So we're going to see much simpler examples than just this, but I feel like I need to mention that there's many algorithms out there that you could describe them recursively or you could describe them iteratively. So what exactly, like, what is the structure of a recursive algorithm? So very often they take a specific form, and I think it's really helpful to think about it in a way like this. Is because remember, when we're going to be trying to define a function in terms of itself, or equivalently, we're talking about an algorithm for which parts of the algorithm call upon recursively itself. And we're going to see how this works carefully, okay? So recursive algorithms consist of two parts. So keep in mind, this is just meant to be an overall structural plan for how you might consider a recursive algorithm. It's a good kind of, I would argue, like construction plan for a recursive algorithm if you're designing a program that uses recursion, or you're coming up with a recursive algorithm. These are two natural ways of composing them. So the first one, sometimes this is the trickiest part, is the recursive case. I must stress that you can have more than one of these cases, but the point is that there's a recursive case. This is where you have a solution. So when you attempt to solve in the recursive case, what happens is a solution is expressed in terms of solving a smaller, and I use quotation marks around smaller, okay? A smaller version of the problem. A smaller version of the problem. And just to clarify what exactly that means, because we would like to be able to say, I've solved a bit of the problem, but I want to pass the buck on to somebody else that knows how to solve the problem, right? So very naturally, this recursive case, what it'll do is it'll take your solution, it solves a bit of it, and then it passes along to somebody else to handle it. Usually this is what we call the recursive call. So, which is then solved via a recursive call. So when I say recursive call, I'm talking about when you call the subroutine or call the function again remember, we're describing things in terms of ourselves. So we haven't really seen any examples of this, so please just hang on very closely. We're going to walk through this carefully. A recursive call on the smaller input. So we have this recursive case. So this is the one that's going to call, or these are going to be the situations where you call the algorithm of itself, right? You're going to solve a smaller version of the problem. And then the other part is when you know how to solve the problem directly. The base case, and you may have multiple base cases. So a way to solve the problem is presented. It's presented without reference to itself. So there's no recursive calls here. So I must stress that the problem that we're talking about is a sufficiently small one. So for example, it may be the case that you know how to solve the problem when you only have, say, one element to consider. Or you may know how to solve the problem when you have a small enough sized input. Or it may be the case, for example, say if we're talking about something quite practical, it could be the case that there's an algorithm for which you could describe it recursively, but when the input gets small enough, what you're examining, you might want to use a different algorithm that you know how to solve that problem directly. So this actually quite often happens when you take and combine sorting algorithms. You take this big complicated input, a very big long one, and then you may break it into smaller chunks, but when they're really small, they might be really easy to solve directly. So that's another way you can view the base case. So very often it's helpful to think of recursive algorithms into these two pieces, and identifying these two parts can be very helpful in thinking about how it's actually solving the problem, if it does. Because remember, I could give you an algorithm, it may not work correctly, but I need some way of thinking about that. Now, it doesn't have to be where you have to think about, oh, I do this and I break it down to a smaller and smaller and smaller case until I get to the base case, which is one natural way of thinking about it. There's types of algorithms called divide and conquer algorithms that do something like this, where what it does is it takes the problem, subdivides it into smaller pieces, and keep in mind each one of these recursive calls will keep repeatedly passing the buck on to somebody else to solve the problem until it's sufficiently small and you may solve that one directly. That's where the base case kicks in. So then you solve each one of the smaller pieces. The point is there's still a conquer part for which it combines all of these answers to get an answer to the overall problem. That's why it's called divide and conquer. But it has a different, not every recursive algorithm takes on this form. For example, it also could be the case that you begin at the base case and you keep repeatedly applying the recursive case to build up an answer. So that's another way you might think about this. So you can think of this like you start at the top. You think a very top-down way of thinking about recursion. You imagine you have the whole problem, you break it to, you take a piece of it, take that and combine it with whatever answer you get from a recursive call or multiple recursive calls until you get down to the base case. So very top-down way of thinking about it. It's very classical for recursion to think about it like that. But you could also think about it the other way around. So sometimes you could have it where you begin at the bottom and say the base case and build up to the answer by repeatedly applying the recursive case. In fact, that's a very natural way of thinking about recursion versus iteration. It's that you imagine you can examine each one of these, but instead of imagining you apply this definition recursively, you may know how to directly solve it. That's where iteration would differ from recursion. So just keep in mind that you can think about this from a top-down kind of process or a bottom-up process. So I thought it would be a good idea I start off with something fairly basic, but I think it also was rather helpful. So let's start off with a pretty cute example, and it's something you could do with your friends. We're going to consider the example of counting. And in particular, we're going to talk about counting our friends. So let's talk about thinking recursively. So let's consider this example where we're going to counting our friends. So here's a scenario. Here's a scenario, just like I have over here. Imagine you have your friends lined up so that you're able to count them all. So suppose you ask your friends to line up. So they're right beside each other, kind of like what I have right behind me. See, the behind me is over here. Having way too much fun with this. Suppose you ask your friends to line up. How many friends do you have? Now, there's at least a couple different ways you might approach this. Now, before we get thinking about this recursively, I thought we would just see the contrast this, how we might approach this iteratively. Does anybody have any suggestions for how we might approach solving this problem iteratively. So just as a reminder, iteratively simply means I have access to all my friends here, and I'm going to use the idea of examining, say, each member of my collection, whether this be through for loops or while loops, those types of structures, those types of control structures. So how might you go about this iteratively? Are there any suggestions? Well, if there aren't any suggestions, I'm going to kind of lead you in one direction here to think about. Well, imagine I'm here, and I don't know, I'm doing some tally work. I got myself a, let me see, I got myself my notes here, but I also have a tally. I could take a tally on my notes. Well, what I could do, akin to something along these lines, I can imagine I can line up my friends like this, right? I can iterate over each one of my friends, and I can count up how many there are, how many friends I have. So I could go over here and I could just examine each one of these, and I can put a tick on my piece of paper and keep a running total of how many friends I've tallied up. So this is how you might solve this problem iteratively. And whatever you get at the end, after you tallied up your running total here, when you have your whole running total, you return that number. See, it's pretty natural, right? So you just count through all your friends. Tallying up how many you have found, and return the total count. Right? That seems so you can easily implement this with using for loops or while loops. So that's one way you could solve this problem. So imagine I give you line up some group of friends and I want to count them up. I can do this, right? With a sufficient amount of paper, I could most certainly accomplish this. Now, let's think about this recursively now. Let's think about this recursively. So I want to come up with a process for which I can determine how many friends I have among all my friends. See, I've got my dinosaur friend. Oh yeah, and I also have another dinosaur friend, but this dinosaur friend is much brighter green. I like that. I love all my dinosaur friends. I love even my Ninja Turtle friend and my cowboy friend. Love all my friends. So what I would want to consider is some process for which I could potentially delegate the task of tallying up to my friends so that I can get a total number of how many friends I have. Well, I want you to think back, and maybe you experienced this in school. I know I did, but in grade school. But you most certainly could try an idea like this. So, for example, if you're getting a handout in class, so sometimes you're given a big stack of papers. What do you do very often? You take one and you pass it along, right? So you take one of these notes, you pass it, and then you pass along the rest. Well, maybe we can use an idea kind of like this to find out how many friends I have. Now, instead of it just simply being that I'm going to pass along the rest, maybe I might want to think about this instead like this. So one of my friends knows, in fact, they're one of my friends, right? And they know to their right, no, this would be to their left, to your right, you see that all the rest of my friends are here, right? So if I look from here to your right, you see that I have 3 more friends, right? But likewise, from any one of these, I could ask a very similar question, right? So for example, if I ask my cowboy friend, well, how many friends do you have to your, to your right? To this way. Well, there's me, and there's anybody that's to the right of me, right? Right? So now we might have a nice way of thinking about this, because all I have to do is once my friend finds out how many friends that I have, including themselves, they can pass that information along back to each of their friends to your left. To your left. Until they can report it back to me. So you can even think about this like you're passing along the tally sheet to them to keep track of this information. So let me give you kind of the breakdown, then we'll walk through an example of what I'm talking about here. So we have a recursive case. So I'm going to abbreviate with rec here. A recursive case is if there is a friend to your right, ask how many friends there are. So all you have to do is return this number plus 1. And this is because you are a friend, right? The plus 1 is yourself. So, for example, suppose that I'm over here and I want to find out how many friends I've got. I'm going to start off by asking the question to my friend over here, my lovely green friend here. My lovely green friend would say, well, I can always ask to the right, my friend, how many friends there are. And whenever I get the answer back, I can just add 1 to that. So I'm going to pass that information along to my first dinosaur friend. And I can ask the dinosaur, hey, how many friends are there? Well, I can always ask my friend to the right. And when I get the answer back, I can just add 1 to it, right? So far, now I'm asking my cowboy friend, okay, well, how many friends do I have to the right? Well, the answer is simply going to be whatever I get from my friend over here, and I'm just going to add 1 to it. So I do the same thing, I get my other dinosaur friend, this Yoshi. So if I ask this dinosaur, how many friends do you have? Well, there's something interesting here. Notice that this dinosaur has no friends to the right. Do you see that? So it means that we know actually how to solve this smaller problem directly. So should I employ the recursive case again, or should I describe this directly how to solve it? Well, do you see how when our recursive case, I ask how many friends there are to the friend on my right, right? But I don't have a friend to my right, so I know how to solve this directly. I just count myself, right? And I could pass. Then when my cowboy friend wants to get the answer back from my green Yoshi friend here, they know the answer, right? So naturally, we could describe this as a base case when I don't have any friends to the right. So otherwise, we just simply return 1. And this is just for yourself, right? There are no friends left to count to the right, right? So now let's walk through this again now. So now that we've actually walked all the way over here, and our green Yoshi friend here has determined, based on how we define the base case here, does everybody see that? Is that we know there is 1 friend. The cowboy friend gets back the answer from the friend to the right. Cowboy knows that there's one friend to the right. Cowboy says, hey, look, that includes me. So now I have 2 friends. Now I could give it to the other dinosaur. I know, sorry guys. Sorry, I'm sorry. You're the other dinosaur, okay? Now, I pass along that. Now the answer from the cowboy back to the other dinosaur. Now, there are 2 to the right of the other dinosaur. Then I just count. I guess the other dinosaur counts themselves, I guess. Him or herself. Then, now I have 3. And the Ninja Turtle now says, hey, cowabunga, guys. And I got 3 to my right, and I consider myself radical. And hence, gives back the answer to me. And the answer to me is how many? 4. I thought it would be a good idea we see another basic example so that we could get ourselves wrapped around this idea of having a recursive case and a base case, and thinking about it in contrast to iteration. So let's consider another example. We'll call this summation. So consider the sum 1 plus 2 plus 3 plus all the way up to some positive integer. So that's like 1, 2, 3, 4, any number that's bigger than that. That's a whole number. And so suppose I want to evaluate what this sum is, given n. So I would like to know that. So we can evaluate this in a couple different ways. Can somebody give me a suggestion for how I could calculate this? And I'm not looking for the clever answer. I just want to know how you'd use iteration, so for loops or while loops, to do it. Any suggestions? Hey, let's write down some actual code that would actually do this. So suppose I have a function that's going to return an integer, and I'm going to call it iterative sum. And it takes in an integer n. So what I'm going to do is something quite similar to actually what I did in our last example. So I'm going to keep a running total. So I'm going to have something, a variable I'm going to call sum. So I'm going to call it int sum, and I'm going to assign it 0. And then I'm going to have my for loop. So naturally, if you actually think about it, I could go through each one of these values and add it to this running total. So here we go. So I can go for int I is assigned 1. I is less than or equal to n. I plus plus. So I'm going to increment I. And then all I have to do is I can just assign sum to be sum plus whatever the value is, right? Because this will go through. So I just really just need something just this basic. So notice every time I takes on each one of these values, and I'm just going to keep it included into my running total, right? And I can simply return the running total when I'm done. It should remind you a lot of our example of counting up our friends iteratively. So I'm sure this is what you were thinking about when I was talking about iteration. Did I get anybody's guess? But yeah, you could put this, for example, into something like C++ or Java. Say if you're using a, if this is just a method, it's not a static one, but this will certainly, you could pump into something like C++ and check her out. So now let's think about this in a different way. So this is how you might approach this iteratively. How might we think about this recursively? And I want you to think back to our previous example. And oh no, I knocked Yoshi over. I'm a monster, everybody. See, our Yoshi friend, I'm going to make sure I put Yoshi over here. So let's think about this in a somewhat different way, okay, everybody? So remember, in our example where we're counting our friends, remember I looked and I said, hey, look, if there's a friend to your right, increment it always by 1, and then it's whatever, how many frames you got to your right. Well, we can do something kind of like that here too, right? Well, let's think about this now. So we can think about summing n integers recursively. So let's think recursively. So I want to think about this now from so you know how I wrote 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus n, right? Imagine I start off at n. So let's start, and I must stress you don't have to do it this way. I just want to show you an example for which I start at kind of like what you would imagine is at the end process as opposed to beginning. So start at n. Then, do you notice that if ever I wanted the answer to that total sum, it's the same as me saying, you imagine you start with n, then add to it everything else. So n minus 1 plus n minus 2 plus all the way down to 1. Right? So you'd agree with me that if I added these two things, I get 1 plus 2 plus 3 plus 4 all the way to plus n, right? The thing is, I just don't know how to do this. Okay, if I'm clever enough, most certainly I do, but I could show you how you could think about this recursively by passing the buck on to somebody else, whom will eventually get an answer to the question of how to add them all up. Well, think about it. Well, what's this? What's that? Let's continue this process. So this is just simply n minus 1 plus n minus 2 plus n minus 3 plus all the way down to 1, right? Pretty interesting, right? So notice that now I have a way of thinking about this by decomposing my problem instance into smaller chunks like this, where what I'm doing is I could imagine I have like a total of how many I currently have, but notice that if ever I want the answer to all of it, I can always break this down into a smaller piece and pass the rest on to get added, namely this part, just like this part. And I can keep doing this. So I can have n minus 2 plus what would go right here? Well, it would be n minus 3 plus all the way down to 1, right? And you can imagine eventually you're going to hit 1. Eventually you're going to get 1. So eventually you're going to have it where you're just going to have whatever the answer is just going to be 1, right? It's eventually going to get there. So this gives us an interesting case to think about here. So we know how to actually answer the question by performing what we call the recursive call. So whatever the answer is, for example, here is n plus whatever the answer is to that. What's the answer to this? Well, it's this plus the answer to that. Well, this is another recursive call, right? Well, what's the answer to that? Well, it's this plus all of that. Well, you can keep doing this over and over again until I eventually only have 1 to add. So this should remind you a little bit about how I pass the buck on to somebody else. Namely, like on my friends, I always would ask my friend to the right. In the same way, I'm just passing the rest of this off to, you can imagine these at each number like a friend. It's a friendly, good old time, right? So here's how you might approach this now. So you can imagine I'm going to write it again in code, so you can actually see this as code. So you got rec sum, and you imagine I take in an integer n. So I must stress that n is a positive integer. And remember, when I write this out, I want to identify the base case, or if I have multiple cases, multiple base cases. So it's usually a good practice to identify and comment these specifically, so that way it's helpful for the reader. You don't want them half guessing what you're up to, okay? You want things to be clear. That's why we would like to have clear ideas when we're thinking about this stuff. So if n is equal to 1, you know the answer to that is 1, right? So this is your base case right here, just like I have over here. You know the answer here is 1. So here you're just going to return 1, right? Right, everybody? We know the answer to that. Okay. Otherwise, this is our recursive case, and this should remind you of what we got over here. What I said was, hey, look, whatever I have the number, and I add to it the rest of the sum. So what exactly am I saying when I do this? When n is bigger than 1? Well, it's n, whatever that is, right? So we're gonna, the answer, as we said, so I'm gonna return whatever that is. It's going to be n plus, how do I write down, add up all the rest of the numbers that are smaller than my number? How do I write that down? Now this is where the recursion part of this, how I said, remember I talked about this idea of having it where we use the same name of the function and we're just calling it on a smaller input. A smaller input, or you can visualize or figuratively imagine you're taking, I guess the better word would be conceptual breakdown of the problem into a smaller piece. So it doesn't have to be literally a chunk that's smaller, it just has to be that we're taking and solving a smaller problem. Smaller. We never want to have it where we're just trying to solve the same thing over and over again. You'll find that we'll run into a lot of problems if we start trying to do that. We're not actually incrementally improving our solution here. We're not trying to solve the problem in that case. We're just going to keep trying to solve the same thing over and over again. So this is where you're going to get your recursive call, everybody. So here, I'll just go, this is where I'm going to call recsum. So please note that that's also the name of this function or method. So what would I write right here? What would I write inside here? What would I write there? What's going in the parameters here? There's only one, but what's going to go in there? So remember, I take whatever the number is, and then I want to add up the rest of the numbers that are smaller than it. But how would I describe that recursively? So think back to our example with our friends. We'd ask the question to our friend to the right, and for which they would give me an answer. But let's keep this now specifically to discussing this function. So I'll give you a hint. It won't be n right here, because that will mean we're trying to solve the same problem again. We want to solve a smaller problem. But what does the smaller problem look like? Well, what's the big, so what, to solve this, well, what is that? So that's us adding 1 plus 2 plus 3 plus 4 all the way up to n minus 1 as opposed to n. So it's one less number. So right here, this is where you would have n minus 1. This is our recursive case. And naturally, that completes the function here. So this is actually a recursive way of solving the same problem. So are there any questions at all about our example here? So you might be staring at this a little like gawk-eyed about this, because there's a couple interesting things happening here, namely, well, there's no other variables right now other than, okay, there's n that gets passed along. There's this function call that has the same name, but don't let that throw you off. It's still a function call. It's just like any other function call. It just has the same name and the same parameters. Just the inputs to those parameters are different. They're smaller. So one thing, actually, let me just show you an example of us going through this example here. So suppose that I wanted to go, say if I wanted n as 5. So if I put in n as 5, this would say that to get the answer to this, I would go 5. Remember, this is 1 plus 2 plus 3 plus 4 plus 5, right? So how exactly would I do that? Well, according to this, what I would do is do the following. I would do 5 plus, well, the recursive call would be answering the following question. 4 plus 3 plus 2 plus 1. So that's what rec sum n minus 1 would be. So this is what rec sum 4 is. So we now take rec sum 4, and to answer this question, we have to answer rec sum 4, which this is 4 plus whatever rec sum 3 is, right? But what's the answer to that? Well, the answer to this is 3 plus rec sum 2, right? But what's the answer to that? Well, the answer to this, now remember, each one of these is a function call, so each one's going to execute this function. But it can't finish until this line can be completed, right? Just in the same sense as we're talking about the M word, the mayonnaise, why I can't just simply just say, oh, well, I'm done here. I could just, we aren't done until the computation is completed. So we got 2 plus rec sum 1. But what's rec sum 1? Well, we know the answer to that is 1, right? So we got 1 plus 2. Well, the answer to this is 3. Then we could pass that back up this way. So now we have 3 plus 3 is 6, right? 6 plus 4 is 10. And now we have 5 plus 10 is 15. So that means the answer is 15. And that should be what we expect, right? Because 1 plus 2 is 3. Then we have plus a 3 is 6. Plus 4 is 10. Then plus 5 is 15. So hopefully my arithmetic is correct, and we should get the correct output of 15 in that example. So we're going to talk more about this eventually, how this exactly works on the computer, at least at a high level. But we're going to now see another example. Are there any questions about this guy here? There's nothing too scary about this, right? Remember, it's just like our other example we had where we're counting our friends. Just the difference is now we're counting them as numbers, as opposed to it being like one atomic unit. Now each one is representative of a number. So I'll include in the notes an example where instead of thinking about these as 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n, or thinking about it as just counting friends, you can imagine I'm given an array. And I want to go and do the same process again, but I want to sum over all of the elements in the array. So check that out. It'll be very similar to this. Just instead, it'll be indexing at these spots in the array. Oh, late night, late night. Got a late night. That's a long day. So let's head over here. We're going to do another example. Usually I find it's helpful to see a bunch of different examples, just to help you get kind of in this mindset. So right now we're looking at some rather simple examples of recursion, but it's getting used to this idea of thinking about the problems by decomposing them from one bigger problem to a smaller one, or maybe potentially smaller chunks of the problem. The point is, eventually somebody knows how to solve the problem. That's a really important step. That's why we have a base step or base case or multiple base cases, is we need to eventually have somebody that I pass the buck on to, namely one of these calls has to have an answer that doesn't use recursion to solve it, okay? Otherwise, we're going to end the infinite abyss of recursively trying to answer questions we don't have answers to. So let's do another example. Let's consider what is called factorial. Let's consider factorial. So I'm just going to define it for positive integers, though you can technically define it as well for all sorts of different other values. For any positive integer n, we're going to define n factorial. So we usually use this exclamation mark to indicate that. So this is n factorial. So that's how you would read this. Where it's going to look like this. Now, I'm going to deliberately write n factorial in a way that is recursive. Now, if you've seen this guy before, you'll be very used to writing it like this. So you might say, well, I'll just write it off to the side. I haven't yet defined it using recursion yet, but you might be used to writing it like this. N factorial is n times n minus 1 times n minus 2 times all the way down to 2 times 1. So it's like n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. So for example, something like 4 factorial would be 4 times 3 times 2 times 1. So let me define this now recursively. So n factorial is going to be n times n minus 1 factorial. And this is if n is greater than 1. So I have a question for you. This would be what you would call the recursive case, right? Or is this a base case? Well, let me write down the second possibility here. So 1 factorial is just equal to 1. This is when we have if n is equal to 1. So which one of these two? So we have 1 or 2. Which one is the recursive case? 1 or 2? Which one's the recursive case? So remember, the recursive case is where it provides you a solution for which it requires, to answer the question, a recursive call on a smaller part of the problem. So it may take a part of the answer, but it passes along the rest of the answer to you want to get the answer for some smaller part of it. Sorry, I'm getting really excited here. I'm just anticipating an answer here. So 1 is the recursive case. And 2 is a base case. And I must stress that you can have more base cases. For example, if I wanted to define what 2 factorial is to be 2, that's another base case I could define if I wanted to, if n was equal to 2. Just as an example. So just to reiterate what I had said previously. Well, for factorial, you can think of it like this recursively. It's 4 times 3 factorial, right? But to know the answer to 3 factorial, well, what is that? Well, the recursive case says, well, because remember, I just applied the recursive definition of what n factorial is because n is greater than 1, right? So what I've written actually on the board here is actually what we would call a recurrence relation. So this is one way you could also describe things recursively. So in this case, it's literally talking about functions from the M word. Mustard. Well, to answer this question, well, this is just 3. Well, 3 factorial. This is just 3 based on the recursive case. It says it's 3 times 2 factorial, right? Well, to answer this question, well, that's 2 factorial is equal, because it's still the recursive case we would apply because n is bigger than 1. Well, this is 2 times 1 factorial, right? Well, now I do my call here. And you see, okay, well, 1 factorial is just equal to 1, right? This is our base case right here. I know the answer, right? For 1 factorial is 1. So now, because I know the answer is 1, I can work back to answer each one of the questions, right? Each question being a recursive call. So now I know the answer to this is 1. So this is 1. So 2 times 1 is 2, right? So this is 2. Well, 3 times 2, well, that's 6, right? So to answer 3 factorial, it's 6. And 4 times 6 is what? It's 24. So this is... The point is that every time I get one of the answers, I can pass it along to answer the question for each one of these. So notice that I break the problem down in this case to a smaller and smaller and smaller example until eventually I know exactly how to directly answer it, right? And then once I have that answer, I can pass that along just like when I was talking about adding those numbers from 1 to n. Notice it's quite similar. It's actually quite similar, right? It's just like it, except now we're just multiplying, right? Now we've called it also factorial. So let's write down what this would look like as an algorithm. So I'm going to write this one a little different. So this time instead of writing just code, I'll write this as pseudocode. Just so you can see how we're kind of building up to different ways we could describe a recursive algorithm. So far we've seen how we can write it as an actual part of a program. And now, let's write down what this algorithm would look like. So just before anything, to perform this iteratively, you just use a for loop quite similar to actually how we did for our sum example, right? Except now you'd just be multiplying instead. You start off at n, you just keep multiplying by each successive one downwards or upwards, depending on how you set it up. If you want to start at n, you work your way down, but you decrement what I would be. As opposed to starting at 1, you would increment I, but you would multiply instead of adding. So let's describe an algorithm here. We're going to call the algorithm fact. And it takes an n. N is going to be a positive integer. Now, to keep this simple, I'm also going to make it so it works also when it's non-negative. So we defined it over there for being, we defined it for positive integers. I'll allow it to be non-negative here just because I know somebody's like, well, 0 factorial is equal to 1. Well, why can't you just simply include that? So I'll just add it in there just as an extra flex, okay? So, and the output is going to be n factorial. And I'm going to note for you that 0 factorial is equal to 1. So if n is bigger than 1 or strictly larger than 1, then, so as we described earlier, so notice I'm just translating the recurrence relation into an algorithm in this case. Some cases it's not very straightforward how to do that. In this case it's really easy. So if n is greater than 1, then we have our recursive case. So here, we have that. Otherwise, we're going to have the base case, right? I haven't put anything in here. We're going to figure that out. We know for the base case, we're just going to return 1. That's what we've established already, right? Well, what's going to go right here, though? What's going right here? Well, to answer the question of what n factorial is, recursively, we said what? We said what about it? So let's head over here. So what did we say, everybody? The recursive definition here was that n factorial is equal to n times n minus 1 factorial. So, what should go right here then? And remember, the answer to n minus 1 factorial is going to be described in terms of our algorithm's call to fact. So you know it's going to be whatever the number is times, well, the answer to n minus 1 factorial would be calling fact on what? N minus 1. And that's it. So notice it's very simple. One thing that's rather deceptive at first is the fact that you don't see loops or anything like that. It's because of the way recursion works in this case. And you'll find that if you walk through an example like this, you might find that it will actually remind you a lot of if you took its iterative counterpart using a for loop. If you took it one step at a time, just there's a mechanism underneath this that, just similar to actually our example we did before, that is going to keep repeatedly trying to solve a smaller and smaller problem. So that's why each one of these calls corresponds to something else, which we're going to talk about. So, just as a remark about iteration versus recursion, and I must stress that the versus is rather superficial. You shouldn't see these as competing paradigms. They're things that you should consider being things that you might consider in both ways. You may have an algorithm that uses both. So, for example, you may have a base case that maybe uses iteration, but it's only because it's a sufficient size that is easy enough for you to solve it directly. That's one way you might use a base case, but you'll find very often in divide and conquer algorithms that the size of the input will become something that is small and constant in size. But in practice, you might find some way of kind of trading off between a recursive version of the algorithm versus its iterative counterpart, or using a different algorithm that's iterative, as I discussed before. So you can view recursion like an alternative to iteration. So don't look at it like there's one exclusive tool in town here. The point is that if you have a recursive algorithm, you could write that using iteration and vice versa. However, I must stress, it must be stressed, that iterative algorithms based on recursive algorithms may not translate naturally. And I'm using that rather subjectively, and vice versa. So just to reiterate my point, if I give you a recursive algorithm, there's going to be an iterative counterpart to it, but to create that, it may be nice and simple, such as some of these examples over here. You can see very natural ways to rewrite that using a for loop or a while loop. But for some sufficiently complicated recursive algorithms that rely on the recursive structure of some underlying mathematical object, such as like a tree or anything like that, you may find that it's not quite as simple as just simply replacing things with for loops or while loops. You may actually have to simulate the recursion. So just keep that in mind. So I want to give you another example, just because we've seen always ones with one recursive call. And I just want to show you that it doesn't have to look like that. So let's do another example. This is a really well-known number sequence. There's several different ways you can define the Fibonacci numbers. So it's a well-known sequence of numbers, and it works like this. So we're going to define fib of n to be fib of n minus 1 plus fib of n minus 2 if n is greater than 2. And we're going to have fib of 1 equal 1 and fib of 2 equal 1. So just as an example, just so that you can see how this works a little bit, let's start off with, so we have the first two Fibonacci numbers here. Now I must stress that you could also define it where the first Fibonacci number is a 0, but we're going to keep it like this. So we would have 1, that's the first Fibonacci number. This next one is 1, right? That's what fib of 2 is. How do we compute fib of 3? Well, yeah, all you do is fib of 3, so it says fib of 3 is equal to fib of 2 plus fib of 1, right? So it's 1 plus 1, which is equal to 2. So that's the third Fibonacci number. How about fib of 4? Fib of 4, it says that that is fib of 3 plus fib of 2, right? So that's 3. How about the next one? Well, fib of 5 would be fib of 4 plus fib of 3, right? What's happening? What's happening? Just keep it very simple. When I look at this 5, it was always because I added the two previous Fibonacci numbers. So if 2 plus 3 is 5, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. And you can keep this process going as long as you like. So let's write down this as an algorithm with pseudocode. And you'll see that this is actually not too terribly scary, right? Because we have a recursive definition of Fibonacci here. So we got our algorithm. We're going to call it fib. And we're going to take in a positive integer. And it's going to compute the nth Fibonacci number. So, what's a good place for us to start for describing the algorithm? Well, a very natural place would be to start at the base case here. You don't have to go with the base case first. You might write the recursive case first. I'm just going to describe with the base case just to show you that it doesn't have to be recursive, base case, or the other way around, as long as you're careful with your control structures. So if n is less than or equal to 2, then we know the answer to the question, right? Fib 1 and fib 2 are both 1. So I'm just going to return 1 in this case. So if n is less than or equal to 2, we just return 1, right? Piece of cake. That's your base case. Otherwise, we have the recursive case. And how do we answer that question? Well, we're going to return the answer to the question. Well, the recursive definition says you add this one to that one. So let's just do that here. Fib of n minus 1 plus fib of n minus 2. And there we go. That's it. So notice that you don't just have one. You can have many recursive cases and many recursive calls that might happen. Just you don't want to have too many because then it gets a little difficult to know which one is doing which, unless you have a very specific and exact way for which that is occurring, like this. However, I must warn you that when you do things like this, to calculate out the nth Fibonacci number using this recursive algorithm, I got to show you how this plays out. So remember that the order of these calls may matter for which one finishes first out of these two recursive calls. But the point is to get the answer of fib of 5. To get that answer, you need fib of 4. And you need fib of 3, right? But to get the answer to each one of these, I have this one, I need the answer of fib of 3. And this one, I need the fib of 2, right? To get the answer to fib of 3, I need the answers of fib of 2 and the answer of a fib of 1. Well, the answer to fib of 2 we already know, right? That's just 1. But you can do the same thing, because notice that fib of 2, that's just 1. Fib of 1, that's just 1. You can get the answer for this one right here. But do you notice now that because we have more recursive calls, in fact, we have several that may potentially occur here, which I want to mention something about. But let me just finish writing out what some people would refer to this as a call tree. So notice every single time I'm showing you each one of the function calls for our algorithm. So it's each one of that's the initial call. Each one of these is a call on fib. So in this case, we have fib of 2 and fib of 1. So this is what you would have to calculate to get fib of 5. So notice how many function calls I have here. You might ask, Dan, how many at most are there here? Well, notice here that every single time you have 2 calls at most, right? Each one of these, you have 2 calls at most. But notice that it actually skews that direction. So notice it's more heavy in that direction, the number of calls that happen. But notice every single one of these does at most 2, right? So for example, here, I have, to get fib of 5, I do at most 2 calls, right? In fact, there's at most 1 function call you could argue this is kind of like this is a tree-like structure. In fact, it is a tree. You have 1 function call here. On this level, you can see there's at most 2. Here, there's at most 4, right? If this were to continue to expand, even though there aren't any down here on this rightmost side, do you notice that there could be no more than 8, right? Do you see that this call tree, the number of calls that are occurring is growing exponentially? So naturally, you might ask, Dan, what does the running time of this recursive algorithm look like? It's not pretty. It's not pretty. This runs in exponential time. So this is actually an example for where you might want to consider iteration as opposed to recursion, in practice at least, or at least to speed up this algorithm. Instead of us redoing a lot of that work over there, instead keep track of that information in, say, an array, and look up if you have the answer already, just like I had my list over here. Say if I already knew what fib of 3 was, rather than recalculating it again, let's just look it up in a table. Then that saves me from having to expand out this whole right side here. I can just get the answer right here. If I knew what fib of 3 is, if I already calculated it over here. You see what I mean? I'll let you think about that. That actually brings to a concept called dynamic programming, which I won't discuss here. But the point I'm getting at is that recursion, although it can make algorithms look really nice and pretty like this, it also may have drawbacks. So you have to think carefully about what the algorithm's doing when you describe it like this. Just like if we're talking about iteration, it may be a really ugly looking algorithm, but it might be faster. I'm not quite sure. It depends on the circumstance. But yeah, that's the basics of recursion. So hopefully you found these examples pretty helpful.